All right, good morning. Can one of you please confirm that I'm audible? Okay, great. All right, so in the last class, we were discussing scalar quantization, wherein we're dealing with lossy compression of a single random variable. And although we did not get an expression or a closed form solution to what is the minimum possible expected distortion possible for a given k, I still gave you a practical algorithm which does reasonably well. So the Lloyd-Max algorithm tries to find a quantizer in the following way. You first fix alpha 1 through alpha k and alpha m and x1 hat through xm hat. These are the alpha i's are the thresholds and the xi hats are the various levels. And we chose at each step, we chose alpha I to be xi hat plus xi plus 1 hat by 2. So basically the average of two adjacent levels, right? So the threshold is basically the midpoint of two levels, right? And we obtain the levels by minimizing the mean squared error for a fixed alpha I. Right? And we saw that the minimizing xi hat is given by this particular formula. Right? So can one of you tell me what the right hand side is equal to in terms of the random variable x? Yes, anyone? It's the mean square. It's not the mean squared error. You're close, weighted mean, but something else. It is some kind of a mean, but what exactly is it? So this is the conditional mean or the conditional expected value of x given that conditioned on the event that x lies in the interval uh, alpha I to alpha I plus 1. Right? So, so note that the denominator is basically the probability that x lies in the interval alpha I to alpha I plus 1. So the conditional probability density function of f of x given that x is in alpha I to alpha I plus 1 is just f of x divided by probability that x lies in alpha I plus 1, and the conditional mean of x given that x lies in this interval is basically this. It's the integral of x from alpha I minus 1, whatever, alpha I minus 1, alpha I. Right, so it's the conditional mean of x given that x lies in the interval alpha I minus 1 to alpha I. Right, so basically at each step what the Lloyd-Max algorithm is doing is you choose alpha I to be the mean of adjacent xi hats, and the xi hat is chosen to be the conditional mean of x, given that x lies in the interval alpha I minus 1 to alpha I. After all, we're trying to find a representative point or a reconstruction point for the interval alpha I minus 1 to alpha I, right? And the minimizing and the xi hat, which minimizes the mean squared error for that particular interval, is simply the conditional mean of x, given that x lies in this interval. Okay. All right. So, any questions? Any questions? All right, so the plan for this lecture is the following. I'll give a very brief introduction to vector quantization and the lossy source coding theorem. And then we'll do perhaps a quick recap of all that we've seen in this course. And if you have any questions regarding any of the topics that we've covered so far, I can address them there. Okay, so the vector quantization problem is the following. Now, instead of doing symbol-wise lossy compression, we're trying to do block-wise lossy compression. So we're given a sequence of length n, let's call it xn. We'll assume that xn is IID distributed according to some PMF px or according to some density fx. So our goal is to construct the quantization and the reconstruction algorithm, which makes sure that the length of the compressed sequence is as small as possible. So Ck is the compressed sequence. So it's a sequence of k bits, and from the sequence of k bits, you obtain a reconstruction xn hat. Right, and the goal is to design the encoder and the decoder such that which minimizes the rate or the asymptotic rate given by k over n, subject to this distortion constraint. So we want to make sure that the expected distortion is less than or equal to delta. So obviously the minimization problem depends on what distortion metric you choose. Okay. So this is almost the same as we had in the lossless compression problem, except that instead of having a probability of error constraint, or instead of ensuring that xn hat is equal to xn, we're tolerating a delta amount of distortion in the reconstruction. Right? So Shannon showed the following. This is now called the lossy source coding theorem, and he said that the minimum rate of compression for an IID source is basically so if there is no loss allowed, if we want to do lossless compression, then we know that the minimum rate of compression is equal to, or the minimum asymptotic rate of compression for an IID source is equal to the entropy. So obviously, if we are trying to do lossy compression, then clearly we should be able to achieve an even lower rate, right? And in fact, this is equal to the minimum of the mutual information, where this minimization is taken over all py given x, such that the expected distortion between x and y is less than or equal to delta. All right. So we're given the input distribution px or fx, and so this is for a discrete distribution, or For a continuous random variable with a density, then it's the minimum overall fy given x, such that the expected distortion between x and y is less than or equal to delta of this mutual information, right? So at the face of it, this looks like a rather surprising result because we didn't have this y at all in the problem. But now we're somehow introducing this new quantity y, and, and the minimum rate of compression is given by this quantity. Perhaps a better way of writing this is can minimize this overall possible x hat x. I'm just changing the notation over here. So it's the minimum overall over the mutual information between x and x hat of p x hat given x, such that the expected distortion between x and x hat is less than or equal to delta. So, so although this doesn't tell us how we're going to construct the quantizer, this this expression has a rather intuitive interpretation, and the intuition is the following. So you're given a random variable x, and your goal is to construct a quantizer and a reconstruction algorithm, which gives you an x hat, right? Uh, and you want to, and obviously you want to ensure that the average distortion between x and x hat is less than or equal to delta, right? So and our goal is to find out what is the amount of information that needs to be stored uh, about x hat given a random variable x, right? And that turns out to be equal to h of x hat minus h of x hat given x. All right. So firstly, let us ask ourselves the following question: Does this sort of statement even make sense? So we're minimizing the mutual information over all possible p x hat given x, right? Now, if you look at the mutual information I x y as a function of px and py given x. So if I fix a py given x, then then how does the information behave as a function of px? Is it concave in px, or is it convex in px, or is it neither? Yes. So what kind of a function is the mutual information? Is it convex in px? Is it concave in px? Right, it is concave. And recall that the channel capacity is the maximum of the mutual information over all possible px. So since it's a concave function, the maximum is going to be some interior point in general, right? But on the other hand, if I fix px as I'm doing in the lossy compression problem, then what can you say about ixy as a function of py given x? It is convex, right? So it's a convex function, So it's going to be something like this, and therefore, in general, the you can use a convex optimization algorithm in order to solve this optimization problem, right? So you can get an expression. Of course, it doesn't tell you. It tells you what the minimum rate of compression is, but it doesn't give you how. It doesn't tell you how to design the compression or the decompression algorithm. And generally, designing an efficient lossy compression algorithm is not very easy. And in fact, a lot of heuristic algorithms are currently used for lossy compression. Right? So maybe let's just do a quick example. So the proof of the lossy source coding theorem, it can be found in the book by Cover and Thomas. I won't go through the proof since we don't have enough time, but perhaps let's do a quick example to see what this mutual information would look like. All right. So let us consider the problem of quantizing a Gaussian source. So suppose that xn is IID Gaussian, where each component has mean 0 and variance sigma square. Okay. Uh, so what is the differential entropy of x? Anyone? It's close. It's half log 2 pi e sigma square. Right? So this is the differential entropy of a Gaussian random variable. So, and another useful property is that among all random variables with mean 0 and variance sigma square, the Gaussian maximizes the entropy, maximum over all possible fx with mean 0 and variance sigma square. The maximum of the differential entropy is equal to half log 2 pi e sigma square. All right, so this is a fact. So now what we're interested in is the minimum rate of lossy compression, which is the minimum over all possible ixy of fy given x, such that the expected distortion, which in this case is the mean squared error, y minus x the whole square, uh, is less than or equal to delta. Right? So this is the minimum overall fy given x, such that whatever is satisfied of h of y minus h of y given x, or I can write this as h of x minus h of x given y. So this is the minimum over all possible. So So we know what h of x is. It is half log 2 pi e sigma square minus h of x given y, or this is also equal to h of x minus y given y, right? Because x minus y is a deterministic function of so h of x minus y given y is the same as h of x given y. Right? So this is half log 2 pi e sigma square minus h of x minus y given y. So this is this. So this quantity over here, right? So h of x given y. What can you say about h of x minus y given y versus h of x minus y? Is one of them greater than the other or less than the other? What can you say? Right. So h of x minus y given y can only be less than or equal to h of x minus y. Right. So this quantity over here. So overall, this this is greater than or equal to half log 2 pi e sigma square minus h of x minus y. All right. Okay. But what do we know about the variance of x minus y? What do we know about this? We know that this should be less than or equal to delta, right? So what can you say about h of x minus y? Can you say that this is less than or equal to something? So we have a random variable x minus y, right? And we know that in order to satisfy the distortion constraint, so note that this is what we are minimizing over. In order to satisfy the distortion constraint, the expected value of y minus x the whole squared should be less than or equal to delta, right? So now can you tell me, can you give me an upper bound for h of x minus y? Right. So it's less than or so x minus you know that the variance of x minus y the whole of the variance of x minus y is less than or equal to delta, and among all possible densities such that the mean is zero and variance is at most delta, the differential entropy is at most half log 2 pi e delta square. Sorry, it's half log 2 pi e delta. Half log 2 pi e delta. Right? So the differential entropy is upper bounded by this. So therefore, h of x minus h of x given y is always greater than or equal to half log 2 pi e sigma square minus half log 2 pi e delta. Right? So this is just half log sigma square divided by delta. Right? So the minimum rate of compression or min is always greater than or equal to half log sigma square divided by delta, and this is achievable because if we choose fy given x, so fy given x to be Gaussian with uh, mean x and variance delta, then we basically get this. The mutual information will be equal to half log sigma square divided by delta. Right? So the minimum rate of compression is equal to, at least for a Gaussian source with MSE with mean squared error distortion, the minimum rate of compression is given by half log sigma square by delta. And this is quite similar to the expression of the channel capacity, except that it had the channel capacity was half log 1 plus uh, p over sigma square. Right? Any questions? Any questions? Okay, so this is maybe time for a short quiz. The link for the quiz is in the chat box. Just let me know in case you have not got it. So I can take 1 or 2 more minutes. Please submit your quizzes soon. Is there anyone who's yet to submit the quiz? Okay, so I'll stop accepting responses. So if you do symbol-wise compression, then for a dyadic PMF, which is the one given to you, then which of the compression algorithms achieves the least compression length or the least expected compression length? It's the Huffman and the Shannon code, because at least for dyadic PMF, well, the Huffman code always achieves the minimum expected length, but for dyadic sequences, the Shannon code also achieves the minimum compression length. And for the other case, if you want to perform lossy compression of an IID binary source with Hamming distortion, then the asymptotic upper bound is, of course, it's always 1 bit, or h of x bits is also an upper bound, because both of these can be achieved even with lossless compression. So if you tolerate some loss, then the achievable rate can only be lower than that. I have stopped accepting responses. I did announce that I'm stopping responses. Okay, so let's do a very quick recap of what we've seen in this course. At the same time, you can always stop me, and if you have any questions related to the topics that we've covered in this course, I'd be happy to answer them. So firstly, any questions regarding what we've discussed in this class or any of the previous classes? I'm audible, right?
Yes, sir.
So any questions? Okay, so what did we see in this course? We first talked about lossless compression. In particular, variable length lossless compression. We saw that, so we could categorize lossless compression algorithms into various classes, including non-singular and prefix-free and uniquely decodable. Right? And we saw that our goal was to construct prefix-free variable length compression schemes which minimize the expected length. And we also saw that a necessary and sufficient condition for a code to be prefix-free was that it satisfies Kraft's inequality. So I going from 1 through k, or if there are m symbols, then 2 to the minus li should be less than or equal to 1. Right? And we saw that among all prefix-free codes, prefix-free codes for random variables distributed according to px, the minimum expected length has to be greater than or equal to h of x. Right? And then we try to design compression algorithms which let you achieve a compression length close to the entropy. So we saw the Shannon code, where you assign a code word length of ceil log 1 over p of x, right? And then you use the achievability part of Kraft's inequality to design the code words themselves. So these are the code word lengths. And then the Huffman code, right? And we saw that the Huffman code achieves the minimum expected length. The Huffman code is designed using this process of merging symbols together so that you construct the Huffman tree. Right? We then saw the Shannon-Fano LIS code, where the code word lengths are C log 1 over p of x plus 1 bits. And basically the code is constructed by first computing f bar of x, right? You first compute f bar of x and then truncate the binary representation of f bar of x to k of x bits, and that gives you the corresponding code word. And the Shannon-Fano LIS code is also prefix free. Right? So the Huffman code achieves an expected length of both the Shannon and the Huffman code achieve expected length greater than or equal to h of x bits, but less than or equal to h of x plus 1 bits, whereas the Shannon-Fano LIS code achieves an expected length which is greater than or equal to h of x plus 1 bits, but is less than or equal to h of x plus 2 bits. And using the Shannon-Fano LIS code, we try to do blockwise compression instead of symbol-wise compression using the arithmetic code. Right? And we could construct, we could basically, it is essentially a Shannon-Fano LIS code, but it allows you to compute f bar of xn in an efficient manner. We have a recursive formula for g of x. I think this was p of xn. I don't remember the exact formula right now, but yeah, so you have a recursive formula for p of xn and g of xn, and using this you can compute f bar of xn and therefore compute the arithmetic code word, right? And then we saw the Lempel-Ziv compression algorithms, LZ77 and LZ78 algorithms. While the first few compression algorithms were mainly for IID sources, these the LZ77 and LZ78 algorithm are universal compression algorithms for stationary and ergodic sources. And for these kinds of sources, the asymptotic achievable rate using LZ77 and LZ78 is equal to the entropy rate and these algorithms form a basis for most modern compression algorithms. Right? And both the LZ77 and LZ78 algorithms were basically work by parsing the given input sequence into phrases and then encoding each phrase separately. Right? So most modern compression algorithm make use of LZ77 or LZ78 as well as arithmetic codes and Huffman codes. So these are the most popular algorithms used today. So then we also looked at a little bit of lossy compression. And the minimum rate of blockwise lossy compression, or the minimum rate of vector quantization, minimum asymptotic rate of vector quantization, is given by the minimum over the mutual information between x and x hat of px hat given x, such that the expected distortion between x and x hat is less than or equal to delta. So for a given distortion delta, the minimum rate of compression is given by this quantity, and this is all obvious since it's a mutual information. This is less than or equal to h of x, right? And but for scalar quantization, we have an efficient algorithm, the Lloyd-Max algorithm. Right? So, so any questions? Any questions?
Sir, is there any bound on distortion that such that after particular distortion you cannot recover the file?
So certainly this is the minimum. Okay, so it's not in terms of the distortion. So what I have here is is sort of the dual problem, right? You fix the distortion, and you try to find the minimum rate of compression, and you cannot go below the mutual information. So among all p x hat given x, if you try to compress to an asymptotic rate less than, sorry, if you try to compress to an asymptotic rate which is less than uh, this quantity, I of x hat, then you cannot recover the original file even with that amount of distortion.
Okay.
So So note that this is the minimum rate of distortion, and since this is the mutual information between x and x hat, this is less than or equal to h of x bits, right? So for a binary source, uh, h of x is always less than or equal to 1 bit, right? So in the quiz question, the minimum rate or the achievable rate of the achievable rate of compression for any given distortion obviously has to be less than or equal to h of x, and consequently it's also less than or equal to 1 bit, right? Does that make sense? So note that this is something that is expected, because uh, if you want to minimize the rate, then obviously the rate that you can achieve using lossy compression should always be less than or equal to the rate that you can achieve using lossless compression, because lossless compression implies zero distortion. Right? If you're allowing some positive distortion, then you can only compress at a lower rate. So So really, for this particular question, I could have said I could have given any positive distortion metric. I mean, yeah. So even the distortion metric could have been arbitrary and would have made no difference. So instead of Hamming distortion, I could have said something else. So mean squared error distortion, or whatever. Any other questions?
So the rate versus that, so the rate distortion curve, it will be a convex curve.
Yes. So the rate distortion curve turns out to be convex. So you have the rate versus the distortion, whatever delta. So obviously it's a non-increasing curve, because as you increase the distortion, the rate can only decrease. But although it is not completely obvious from this, it does turn out to be convex.
Okay.
It should be clear that it's a non-increasing function. So delta as a function of r, or r as a function of delta. But it also happens to be convex, which requires a separate proof.
So it goes to zero when delta is greater than sigma square.
Sorry.
So it goes to zero when the sigma square,
True.
when the delta is greater than sigma square.
Yeah. So for mean squared error quantization of a Gaussian random variable, or IID Gaussian random vector, the rate or the minimum rate of compression is given by half log sigma square divided by delta. So as long as delta is greater than sigma square, uh, you can make the distortion, you can make the rate equal to zero. Because why? You don't need to transmit anything. The reconstruction algorithm always outputs the zero vector, right? So if and you know that the expectation of x minus 0 the whole square, or xn minus 0 the whole square, is expectation of x square. So this is basically the variance All right, so this is just sigma square. So you can always achieve a distortion of sigma square.
Okay, sir.
Right? Any other questions? Okay, so if there are no other questions, then we can end the class. So this is officially the last class of this course. I'll be expecting your recorded videos next week. I think I've already announced this on Piazza, but I'll make another announcement once again. We'll have some Vivas next week, probably Tuesday, Wednesday. I'll send a separate post. I'll post separately on Piazza regarding the so that we can fix a suitable schedule. Okay, sure. I'll upload these class notes on Piazza as well.